please sit down and we will have the afternoon session of the Crafoord Symposium here in the honor of Eugene Parker. And the first up is Nicola Fox, and she's the Science Mission in the Science Mission Directorate and NASA headquarters, Washington, US, and she will talk about the challenging of exploring our sun, the 60-year Odyssey to the Parker Solar Probe. You're on.
All right, good afternoon. Oh, that was loud. Good afternoon, everybody. Welcome back from lunch. I know, certainly for me, once I've had lunch, I tend to want to take a nap, so I will not be at all offended if you all start to nod off during the talk. I will do my best to make it lively so you stay awake. And so, as Jan-Erik said, I'm Nikki Fox. I am the director of the Heliophysics Division at NASA headquarters. Before I went for that job, I started that about 3.5 years ago. I had the honor of being the project scientist for Parker Solar Probe, and so it is, while I love all of my missions equally, this one is particularly close to my heart. So I wanted to start off, so obviously thanking the members of the Academy and the Crafoord Foundation for inviting me and my fellow speakers to talk about the wonderful work of Gene Parker. And so this is just an animation showing really what we all know that Gene did for us. So you see our planet there being bombarded by particles, by stuff coming from the sun, which of course Gene correctly identified as the solar wind. If I take you now to the top to look down on the poles of the sun, you will see that solar wind actually emanating out from the sun in a spiral shape, and of course we call that the Parker spiral. But not only did Gene discover what was going on at the star, he also later went on to correctly predict that this solar wind itself would inflate our whole heliosphere and produce a protective bubble or a cocoon in which the entire solar system orbits the Milky Way, and so our sun protects us from the Milky Way. Fortunately for us, Gene was fascinated by the sun. So, everyone since the beginning of time has been fascinated by the sun. Even in prehistoric times, even the dinosaurs looked up and said, I wonder what that is in the sky. And ancient Babylonians drew pictures of solar eclipses on stone tablets. We know that the Renaissance astronomers looked through telescopes and watched the sunspots. And then, of course, eventually we took to the skies ourselves and we took to space to fly the cutting edge images that we have. So Gene, having finished his PhD, immediately started working on the sun. Even before he published his paper that we're all really celebrating today, he published works on the prediction of how sunspots form due to magnetic flux rising up and coming through the surface. He proposed the solar dynamo. He even talked about how the sun would affect geomagnetic activity here at Earth, which means that before anyone else had thought about it, Gene had basically discovered space weather. He also talked about solar flares and predicted that large particle acceleration would occur with solar flares, and then went on with Peter Sweet to really describe magnetic reconnection going on at the sun, which we know of as the Sweet-Parker theory. But of course, in 1958, Gene actually wrote the paper where he said, I'm going to call this the solar wind. And as Jan-Erik beautifully described before, all based on the work of Biermann, this corpuscular radiation that Biermann proposed that was actually causing that comet tail to always move away from the sun. Gene then actually said, yep, that's right. Not only is the corona not static, it's actually highly dynamic. And even though sometimes it throws away a lot of material, sometimes less, it's always doing that. So having written that paper, it caused a lot of controversy, as we all know, with the referees suggesting that if you're going to publish in this type of science, maybe you want to go to the library first. And Gene liked to tell me that was the nice review. So I don't know what the other one said. But fortunately, the editor, Chandra Sarkar, decided to publish the paper anyway, saying, you know, I think it's a ridiculous idea, but I don't want to see it killed, so I'll publish it. And then a few years later, the Mariner spacecraft, Marcia Neugebauer and Snyder, who published the paper showing that indeed there was a supersonic solar wind moving away from the sun continually. So Jean was right. So this happened in 1958. It was very significant. I think it was Milan said earlier that that Jean's early career, started with the birth of the space age. So in 1958, we just launched Explorer 1 and discovered that space was not empty. It was indeed very interesting and full of radiation. And James Van Allen had discovered the radiation belts. Jean Parker discovers the solar wind. It was both of these things were so profound that it was decided that we should have a national agency in the US to actually go and do these really big missions. And so you can see there, this is a picture from July of 1958. Dwight Eisenhower, the president, in the middle there, and Keith Glennon and Hugh Dryden, who were the first administrator and deputy administrator of NASA. In July of 1958, Eisenhower signed the National Space Act, which basically gave NASA its charter. As a part of that, the National Academy of Science chartered a committee that was chaired by John Simpson. Ironically, John Simpson, the same John Simpson, Jean Parker's boss, that said, please don't put my name on that paper. So despite that, I know words, they're things that you must regret later in life, hey. But despite having said, don't put my name on the paper was really sort of growing in controversy. So much so that it actually spurned one of the missions that the Simpson Committee report then recommended that NASA should do. So there were 14 missions in that report, visiting each of the major planets. There were a couple about going around the Earth's magnetosphere, a couple for the moon, and one to fly through the corona of the sun. It was called a solar probe. And so in 1958 was the first time that the mission was proposed. And so even though clearly after doing this paper, Jean didn't stop, he went on to do many, many other things, including talking about stellar winds and talking about the formation of the heliosphere that I know Pontus is going to talk about at the end. Many, many other things that he did. But the thing that I am most proud of is that he actually gave birth to Parker's solar probe. So this is an animation of the spacecraft itself, Parker's solar probe. So it took 60 years for us to be able to fly this mission. And clearly it was not because of lack of interest in the scientific community. A solar probe or a mission to go into the sun's corona remained the highest priority of missions throughout those 6 decades. And so many subsequent studies that came out of the National Academy still had a solar probe as the highest priority. There were many, many studies that were done, many attempts to fly this type of mission. They were always unsuccessful, either because technology wasn't there yet, they were too risky, or they were too expensive. And so it took a while, but in the mid-2000s, NASA actually challenged scientists and engineers at the Johns Hopkins Applied Physics Lab to come up with a concept for a solar probe that would not require a big Jupiter flyby, which was the sort of typical way to get there, to go out to Jupiter, do a kick up, come out of the ecliptic and go kind of north-south, very similar to what Ulysses had done. And also did not require to use any kind of radioisotope generator for power. And so the very clever engineers at APL came up with a great concept. And believe me, I can talk for hours about the technology in this mission, but you'll be pleased to know I'm not going to. So I do want to cover some of the sort of transformational things that it took to put this mission into space. One was actually at the clever orbit. So the orbit the orbit is completely in the ecliptic. It does not require going out to Jupiter. It required a huge launch vehicle to give an incredible amount of delta V, so that when the planet, when the spacecraft left the planet, it did not get any sort of influence from Earth. We didn't want any angular momentum in the spacecraft, so we did not want it to be dragged around as the Earth was orbiting the sun. So one thing that we used to say that we were the mission that was always on a diet, because we could not put a pound on. Clearly this is before COVID. So it had to be really, really small and really, really compact. One, because we don't want anything out in the solar atmosphere. We want it all sort of tucked behind the heat shield. So the spacecraft herself, she stands about 3 meters tall, and at her widest point, which is the heat shield at the front, that's about 2.4 meters in diameter. So the heat shield itself is just a marvel. It took about 10 years to do all the technology maturation for that heat shield. It is made of 2 very thin phase sheets. They're made of a carbon-carbon composite. It's a bit like a graphite epoxy, something that you would find in a tennis racket or a nice bike. And in the center of that is a carbon-carbon foam, which is about 97% air when on Earth. Obviously in space, there's the air disappears and it becomes a very hard, rigid structure. On the front side of that heat shield, there is a coating. It looks red there because it's reflecting the sun. It's actually a very, very, very bright white, even like a whiter than white coating. It's an alumina coating, and it's plasma sprayed onto that front side of the heat shield. It has to be plasma sprayed because it has to be super flat. You can't have any bubbles, anything that might be a little bit higher, a little bit thicker, will cause a gradient in that structure. So it is plasma sprayed, and so it is a very, very definite number of molecules thick. The heat shield itself, the front side gets to about 1400 degrees Celsius or 2500 degrees Fahrenheit. It is obviously traveling through 3 million degree plasma. As we all know, the corona is superheated, but the corona is not very dense, and so very little actually gets sort of heat coupled into the heat shield itself from the particles. It mostly has to deal with the light from the sun and the heat from the light from the sun because we're so close. We also use solar panels. So that was the other thing I mentioned. We could not use the radioisotope generators on solar probe. So we went to solar panels. And that seems like a no-brainer. You're going to the sun, you use solar panels. So that would be great, except that solar panels do not like to get hot. And so we have to do a lot to keep those solar panels cool. One thing that we do is the actual wings themselves are kind of they flap and feather, so we can stretch them all the way out when they're by the Earth or around Venus. And then as they get closer to the sun, they tuck in. When we do our final closest approach, when we're within 10 solar radii of the sun's surface, just the very last row of cells will be illuminated. So, on a wing that is literally longer, but maybe twice as long as my arm, the last row of cells is about the size of your fingernails. And just that row of cells will generate the same amount of power close to the sun as the full wing does when it's away. So it kind of gives you an idea of how close you are. We also had to do some state-of-the-art instrumentation. Most of the instruments sit on the main body of the spacecraft, and so they are protected from the solar environment. With two exceptions. I realize Milan's here. I got to talk about the whips as well. But so the electric field instrument has 4 long antennas that stick out from the sides of that the support for the heat shield. They had to be made of a pretty exotic material, a niobium C103 that we had to make those from. Traditional materials will not stand up to the incredible heat that we have to go through. Not just heat, but it goes very close to the sun on one side of its orbit and then out around the orbit of Venus on the other side, which means it goes very hot and very cold. And so if you think about taking any material and superheating it and then cooling it quickly, most materials will change their property and become either brittle or maybe elastic, but whatever, they will change, and we cannot have that. So it took a while to be able to develop or to find materials that would actually stand up to that. And then the bravest little instrument on the spacecraft is the Solar Probe Cup that sits out on the side. You can actually see it. I just realized I have a pointer. So there is the Solar Probe Cup. Peeps around the heat shield, takes no respite from the solar atmosphere. And so that not only did we have to find very good materials, but we also had to suspend all the wires in sapphire crystal tubes to make sure that nothing melts when it gets superheated. Many other things, obviously, in the spacecraft, but the one that I think is really significant. So we talked about the solar panels. We also have to actively cool the solar panels, so it isn't just enough to keep them in the shade. We actually have to cool them, and so we run water through the like in channels between each of the solar cells. We run water through those to actually keep them cool, and that's a complete system that runs through the solar panels, and then it gets radiated out from, these are the radiators here that sit around the truss that holds the heat shield in place. The actual truss itself is a titanium welded structure, and I don't know if there's any engineers in the room, but I've seen engineers get weepy over the beauty of the welds on this thing. It's a fantastic structure, and it was only one company was brave enough to do it for us, so we have our titanium welded structure. The heat shield itself is held onto that structure by just 6 carbon bolts. The reason for just 6 carbon bolts is to make sure we don't conduct any heat into the main structure. Many pieces of technology just holding everything in place. The last thing I'll talk about is that the spacecraft is highly autonomous. We do not have the luxury of being able to control the spacecraft or kind of joystick the spacecraft because it takes light 8 minutes to get from the sun to the Earth. And so if Parker Solar Probe is having a problem, there's no time for us to get a signal, diagnose it, and get the signal back. So the spacecraft has to look after herself. And so she is a fiercely independent, highly automated piece of machinery. So all those things, plus many more obviously, are what made it take 60 years. I noted that she's very small and very compact, which means everything has to be miniaturized. And if you think 60 years ago about the amount of computing power it would take to just be able to do a very small maneuver on the spacecraft, that would take city blocks worth of computing power. Now it's all in little microchips. So let's look at the launch. So this is our launch, Delta IV Heavy, which was a beautiful launch on August 12th, 2018, 3:31 in the morning. She lifted off. It was a perfect launch. So there you can see a really nice shot across the water of that Delta IV Heavy taking Parker Solar Probe up. This is just obviously a simulation. The fairing opens up, Parker Solar Probe comes out, sees space for the first time. We'll separate from the cryogenically fueled second stage of that Delta IV, and then you will see a separate, there we go, that is the final kick motor firing. And then, so that gave us our final Delta V. And then Parker Solar Probe separates from that kick motor out into space, puts out those long solar wings. You can see how long they are there. And then starts to deploy the instruments. So that is the magnetometer, or the magnetic field instrument boom at the back. And then the plasma wave electric field antennas open there. Moving very fast, just about 6.5 weeks after leaving Earth, she will encounter the planet Venus for the first time. We do a gravity assist maneuver at Venus. We actually slow down just a little bit flying past Venus, and it basically turns us in towards the sun. So now you can see that's what the orbit looks like. If you look, there will be 24 of those red circles, and each time we do a gravity assist by Venus, the circle gets a little smaller, or the ellipse gets a little smaller. So we did one right after launch. We've just completed number 4. So we have 3 more to go before Parker Solar Probe ends up at the closest approach. And so Parker has broken many records, and still more records to break. Clearly, the fastest human-made object, the object closest to the sun. And so I would not at all in any way say that we are competitive. We're just hotter, faster, and closer than anything else has ever been. So faster, we'll be moving at a top speed of just under 700,000 kilometers an hour, which is about 200 kilometers a second. So don't try that at home. You will get a speeding ticket. We are closer, so we will get to within, at our closest approach, 6.2 million kilometers from the sun. If I put the Earth and the sun on a meter stick, Parker Solar Probe will be 4 centimeters from the sun on that scale. And then obviously hotter, we are traveling through this 3 million degree plasma and dealing with these huge temperatures. But what I really wanted to highlight in the time I have remaining is some of the science highlights from Parker Solar Probe. A couple of you saw a few of them yesterday, and I promised I would show more today. So here are some of the Parker Solar Probe science highlights. So the first one, several people have already talked about it this morning, are the switchbacks, a possible energy source for the corona. So these were actually seen on the very first orbit of Parker Solar Probe, when we didn't really expect to see anything particularly interesting. But as we were flying in and getting to perihelion, we saw this magnetic field structure, and so if I try and orient you, this is magnetic field strength here. Sorry, this is magnetic field strength here. This is electron density, and so as you see, as we move in, suddenly we start seeing all of these very strange magnetic field fluctuations. And at first, we thought maybe, well, first you worry that the magnetometer is not working correctly. That's the first thing that any instrumenter goes through their head. Oh my God, the instrument's not working. So having shown that the instrument was indeed working and it was fine, it was then, well, what is causing these sudden, very quick reversals in magnetic field? And so, there was a thought that maybe it was due to crossing the heliospheric current sheet all the time. Maybe we were just literally flying right down the heliospheric current sheet and just bobbing up and down. But then when a couple of weeks later we got the plasma data back and able to look at the pitch angle distributions and see that there were indeed 1 or 2 crossings of the heliospheric current sheet, but this was happening all the time, and that the direction of the plasma on the field line was not changing, which meant that the whole field itself had to be doing a big reversal. So we called those switchbacks. I will note that as we've continued to do more and more orbits, we have seen more and more switchbacks. One thing we've noticed as we're closer in, the switchbacks are definitely more prevalent. The S shape, if you like, is larger. These are not small. They're millions of kilometers in size. They actually release a tremendous amount of energy. They are not simple turbulence. They are actually organized. We found that they're kind of ubiquitous in the corona. They tend to organize into groups that are then separated by slow solar wind. So as we continue to study, we will continue to see more of them. We do actually expect, as we get closer and closer, they may actually get smaller and may even disappear, because we're then sort of inside that acceleration region. But for now, we're flying kind of through the heart, as you'll see in a minute, through the heart of the Alphane surface, and seeing kind of the sort of maximum of these. Not only do we think these could possibly be a source of heating for the corona, but we've also found that associated with these switchbacks, and actually indeed with crossings of the heliospheric current sheet as well, that we see the kind of the locations of unexpected accelerated particles. And so by analyzing the anisotropy of the particles during the switchbacks, they were able to determine that the energetic particles themselves do not follow the abrupt change in the field line. So the plasma stays on it, but the energetic particles themselves do not do that reversal. They actually get accelerated and move away from that site. We also see that with the crossings of the heliospheric current sheet also. So whether these particles are accelerated, by a reconnection process or something that's happening in the location of the switchback, or whether it is something, a more distant location, we don't know, and we need to continue to do some more studying. This is actually a very recent result that we saw. You can see the paper there in 22, but this is a recent result from very recent flybys. So it's going to be exciting to see kind of what happens and if we're actually seeing particles really, really energized by these little switchbacks. So maybe it's as they're relaxing into straight again and dumping energy and heat into the corona, whether or not they're also accelerating particles. So it'll be interesting to see more. And then I just added this one in. This is from the ESIS instrument, so the high energy particle detector. You're looking at so this is epi-low, so this is 300 to 200 keV protons, and then this is epi-high, looking at 1 to 2 MeV protons. This is the orbits 1 to 10, and I really like this plot because one, you can see very clearly how we do a Venus flyby, and then the actual orbit shrinks. But not only can you see that, you can also really see how much the sun is waking up. And so you can see how much more intense the later orbits are in all energies. So it's just really, really nice to see the sun waking up. We were very happy to announce in December that Parker Solar Probe had actually flown through the corona and sampled the energetic particles and the magnetic fields there. So this was kind of a milestone when we flew through the Alphane surface. This happened at about 13 million miles, is that right? No, 32 million kilometers away from the sun. We can see here, we flew through these two regions here. You can see the waves and the particles are still bound to the sun. And in this one, they are the gravity and the pull of the magnetic field of the sun is not strong enough to constrain those particles anymore, and so that's when it becomes the solar wind. So this was a very key thing for us to fly through. This was one of our main science goals. I'm not sure if I can get that to go again. Yeah, I can. So that was one of our main science goals, was to actually fly through the Alphane surface. When we were first designing the mission, all of the models predicted that you would have to go to within maybe 12, maybe 13 solar radii before you would actually see this. As we were completing the design of the mission, new models and new results came out that showed it would probably be between 15 and 20. And so this was extremely nice to see this happen. It happened, it was about 8.1 million miles, so yeah, 13 million kilometers away from the sun's surface that we did this. So really exciting. Definitely saw we were under the surface for about 5 hours on the first orbit. So that happened in April of 2021. Yes, April 28th, so nearly a year ago of 2021. And we've continued. We've seen on the next couple of perihelion passes. We haven't published it yet, but we also went through this region on each of the other ones. So just really exciting to be in there. We do have another 3 Venus flybys to go, so we're going to go a lot closer. So we expect to spend a lot more time. And if those of you that were interested, the Alphane Mach number during the excursion into the corona was 0.79. Okay. So I was really, really, really glad, having seen Moira's talk, that I chose this morning to put this one back in. So this again was a very early result for us from Solar Probe. It was one of the earliest orbits, actually the first orbit that we did, when we found a very interesting and unexpected result. Again, expecting to see this a lot closer to the sun, but actually much further away. We found that we saw the change of the flow going from sort of bound to the sun and transverse flow into the flowing radially outwards. And we found that much further away from the sun than we had expected. Not only did we find it further out, we found that the actual transition, it was a much, much, much sharper transition than we expected. And also that the transverse velocity of the magnetic field and the particles was actually about 10 times higher than the models predicted. And so you can see with the sweep model here, there were about 35 solar radii where they made the measurements, and they were finding that this speed here was about 10 times higher than was predicted. And so it's kind of interesting. You know, it makes us wonder, okay, was the young sun rotating faster than we thought it was? Did it have a more violent past than we thought? It's you know, again, it's interesting because it tells us a lot about other stars too. Maybe it tells us about the life of other stars and maybe their transition from fast to slowing down. And so I was particularly fascinated by your talk, and I want to chat to you about that later. But this is a really nice. Again, this is a result that we had very, very early in the mission, much higher altitude than we thought we would see this. So changing the subject and talking about some dust, this was probably my favorite result. And one of the reasons this was my favorite result was because I'm sure many of you know Ross Howard, who is the PI of WISPR. But when I first came on as the project scientist for Parker Solar Probe, I was having breakfast with Ross, and I was asking him about, you know, what kind of things are you excited about with the mission? And he goes, I'm really excited to see absolutely nothing at all. And then explained to me that what he was really excited to find was maybe there would be a dust-free region around the sun, and indeed his camera would show nothing at all. And so I frequently tease him about, are you seeing nothing at all yet? But anyway, we are indeed on our way to looking to finding a dust-free region around the sun. And so, as everybody knows, the solar system itself is awash with dust. It's kind of the cosmic crumbs of collisions and things that have happened from you know, things that have formed planets and asteroids and all the other good stuff. But about a century ago, Henry Russell predicted that, you know, as the dust gets smaller as you get closer to the sun, so it goes through more and more collisions, gets closer to the sun, gets smaller and smaller, that at some point it would actually evaporate because of being so close to the sun. But we've never been able to see it because guess what? You have to look through the dust to see it, so you can't see nothing through something. But when the WISPR field of view, this is our white light imager that flies on Solar Probe, when it got to about 19 solar radii, when the field of view, the inner field of view got to about 19 solar radii, they actually started to see this observation here, which was that the brightness started to dim. As they've continued to move closer and closer, we've certainly see this dust depletion zone happening. They think it will happen between about 5 and 19 solar radii. So far we've got measurements up to about here. So we're hoping that with the next Venus flyby, we will actually get our inner field of view looking even closer and maybe into this dust-free region here, which will be really, really nice to actually be able to finally prove that there is indeed a dust region around the sun. So you'll see me probably again getting very excited about seeing nothing at all. But staying with dust, we also discovered that, or I shouldn't say we discovered it, had been seen by other missions before, but we actually saw the full 360-degree view of the Venusian dust ring. And so it's kind of interesting, when we take the images with WISPR, we usually subtract the dust. So the dust itself, it shines about 10 times brighter than the solar wind. And so the first thing we do whenever we produce the images is remove all of the background. So you remove all the background stars, all the background dust, and then you can see the solar wind. So this particular one was observed during a roll of the spacecraft, and it was to do to manage the momentum on the spacecraft. So they actually did a roll out beyond the orbit of Venus, and lo and behold, because it was in a different orientation, and also because we weren't worrying about taking the images at the time, we didn't do any subtraction. And so what they did see was, so this would be the orbit of Venus marked by those red dots, and they saw a very clear dust signature completely aligned with that orbit. You can also see the Milky Way beautifully in the background there. I feel like, so as I work in the Science Mission Directorate, this is the plot I say has something for everybody, because you can see the sun's corona, so there's heliophysics. You can see some planets, so that's planetary. And you can see the Milky Way, so that brings astrophysics in there too. So that's something for everybody in this plot. And Earth, so there's Earth science as well, quite happily in there. So this was just a really nice discovery, and being able to see it all the way around the whole of the 360-degree view. I'm good. All right. So I will tell you about one more result at Venus, and the reason I like this one is just because we talked about the fact that Mariner 2 was the probe that kind of confirmed the solar wind. So I think it's very apropos that a solar wind explorer bearing Gene Parker's name actually discovered some groundbreaking science at Venus. So what you're looking here, it's the WISPR telescope again, looking, it's actually able to see through the thick Venusian atmosphere and look at the night side of Venus, which is faintly glowing in visible light. And it's faintly glowing because the temperatures are about 735 Kelvin. The darker splotches there are the highlands, the highland areas, which are a little bit cooler, and then the brighter regions are the lowlands, which are hotter. And next to it, you can see the Magellan radar images, and so you can see really good agreement between these two. But this is the first time we've ever been able to image Venus in visible light, so super cool. And then just again to show how the sun is waking up, this is basically riding with Parker's solar probe, looking at what the WISPR camera is seeing. So you can see a lot of dust in here as well as cosmic rays. Here comes a beautiful coronal mass ejection. There. You'll see another one here, and then you'll see a cannibal coronal mass ejection in a minute with, here we go, 1, 2, 3, 4, forming one really nice big coronal mass ejection. So a beautiful image there, telling us for sure that our sun is definitely waking up. So much so, this is another surprising result, was the first circumsolar solar energetic particle event. So this happened just 1 year into the new solar cycle, and any of you who are solar energetic particle people know that these events are very rare. They're actually, it's unusual to have these events, so to have one in so early in a solar cycle is really rare. We were able to determine it was a full circumsolar event because of the very fortuitous placement of all of these different spacecraft. So you can see a Parker Solar Probe, stereo, solar orbiter, and of course our own spacecraft that we orbit the sun on Earth. You can look at the various energies, various observations from the different spacecraft, but certainly told us that this was a full circumsolar event. Now, the energetic particle characteristics were determined by this sort of longitudinal distributed set of observations, and we certainly think it does not support something that would be maybe like a simple expansion of one particle, energetic particle burst and then just expanding around. It's certainly something a lot more complicated than that. So interesting to see, a lot more work to be done, but it certainly suggests a pretty complicated picture of particle acceleration and transport. And so I hope that you've enjoyed seeing some of the results that we've had from Parker Solar Probe. The one thing I'll leave you with is the thought that our sun is definitely waking up. If you've been following the space weather news in the last couple of weeks, you have seen a tremendous number of X-class and M-class flares. A large event in February that occurred that actually really heated the upper atmosphere here and caused the demise of 41 SpaceX Starlink spacecraft, and so definitely it's an exciting time to be with Parker Solar Probe, because not only have we crossed into crossed below the Alphane surface and crossed into flying through the corona, we're going to be doing this at a very active time. So we'll see more and more exciting material, more and more exciting science, and hopefully be able to answer more and more of Gene Parker's questions. So with that, thank you.